Uttam Prabha. Digital India. Educated India.
So today we talk about a very interesting area which is called computational geometry, which is basically a neat field for solving some geometric problems. So anything we do with the geometry comes under this area called computational geometry. Anything we do geometric problem in computer, so that comes under this computational geometry. So this is a very big area. So we'll just introduce this area. What do you mean by we'll take some data structure to solve certain type of problem in computational geometry. Okay, so let us start. So it is basically the umbrella where we solve the geometric problems under this computational geometry. So geometric problem may come from computer graphics, or we may have some simulation of physics, fluid dynamics. So all the areas are having some geometric problem need to be handled, and so for that we need some algorithm to solve those problems. So to solve some geometric problems. So what are the geometric? What are the objects? Objects are basically we can have a points. A point could be in any dimension. This is a two-dimensional point. So on a plane, it could be 3D or it could be 4D. It could be d-dimensional. So a point could be in any dimensional. So this is a object, geometric object, or it could be a line segment. Line segment means it is a line sorry, with the endpoints, or it could be a line. So line means there is no endpoint, so it's just a there is no endpoints in the line. But if there are endpoint in the line, that is called line segment. So these are the basic fundamental object in geometry, and we have given some object, and then we need to have some problems depending on our application. Like suppose some basic structure will just give you some idea of the computational geometry. Suppose we have given some points, and these points could be in any dimension, say 2D points or 3D points. Anyway, so now we may ask for the polygon structure of polygon of this, the closed loop which doesn't intersect, like overlap. So this is a polygon. So we can think of how to given a point, how to make this polygon, or given a polygon we can have something to do. So this is one structure which is called polygon. Another structure could be triangulation. Triangulation means we have given some points, we have to find the triangle of this. So like this. So we form the triangle. So this has very good application in the fluid flow. So suppose we are having some water flow, and we put some particles, water particles there, and we want to see which particle is near to which particle. So for that, so this area finite element method. So there we have some applications of this triangulation problem. And another structure could be we may need to find the convex hull. So this is the closed interval, so which is optimal closed interval covering all the points in a convex hull. Means if you take all the points, if you draw the line, the other points are inside that region. So that structure is called polygon structure. Convex hull. So this also has some applications in the in some fluid dynamics. So this is just a rough overview of the structure of computational geometry, but if you want to do more on that, so this is a very good book on computational geometry by Mark. So this book we are referring here because today the one data structure we will learn which is coming from this book, not from our textbook Codeman. So that's why you can, but we will not cover much from this book. Just for today's lecture, we will just introduce this area. Okay. So now today's problem is what is called orthogonal range search. So what is the orthogonal range search problem? So we have given some points. So points is the object. So we have given some points, and we have to do some searching on this on this database. So suppose these are the database. Each point is having d dimension. maybe some student record, so student record having d dimension, or maybe some information of the ray student. Suppose in a city, in a new town or Calcutta city, there are some ray students over here, and each ray student have some component like the location, so latitude, longitude, and then the average price of the meal, quality of the meal, whether this is a veg restaurant or non-veg restaurant. So all these are will be in a will make one dimension. So each restaurant is associated with. So this is a database problem. So we have some data. So we have some n records. Each is a restaurant, and we have some feature of that restaurant or some attributes. So depending on that, we have some dimension. Now we are interested to know some query. Query means we are interested to given a orthogonal range. Orthogonal means the 90 degree, the right angle. So given the orthogonal range, we want to see who are the points in that region. So that is the thing. So given this box, suppose this is 2D, this could be any dimension. It could be 1D, 2D, depending on the value of this D. So suppose we have a 2D range search. So we have a box for 2D range. We have an orthogonal box which is parallel to the axes. Now the query is, there could be many queries we can do. Are there any points in this box? That means if we have, say, then it is more clear if we go for the 3D anyway. So for 3D, what we have? For 3D, we can have this x, y, z axis. We can have x, y, z axis. If the points are in 3D, then it will be like this. We have a box over here. Yeah. Three-dimensional box over here. Anyway, so anyway, this is a like match box. So we have a box over here. In that box, we want to find the what are the ray student, what are the points belongs to this box. Like one could be okay. This z this axis we can have a average price of a meal, and this axis the quality of food, and this may be whether the restaurant is having some internet or not, Wi-Fi connection, something like that. So we may have another dimension also if we have another attribute. So we want to search few restaurants or few points from this database which is having this which is belongs to this box. This is called range search. So searching means, are there any restaurant in this category? I have a specific category. I want to go to non-veg restaurant with this average meal should not be more than 500 rupees, and then so I have a particular query. I have a particular range. In that range, I want to find all the points, all the possible restaurant there. So this is a nice application. So basically, I want to find all the points which are in this range. So that is called range search. So there could be few type of query. Are there any points? Okay, if there are some points, how many points are there? That is one query. And if there are at least one points, we need to know the points. We need to know the students. We need to know the student who has this attributes. Okay. So this is the problem for today's. So basically, we have some points or records, which is d dimension. Here d is 2 for 2D range search, and we want to do this query in a faster way. Okay, how faster will come to know. So can you suggest some data structure for this? Sorry, can you suggest some algorithm for this? Like how to do it? Suppose we have n points. We have n points, and then we have a box. We have given a box. We have given a range, x-axis, y-axis. Say for 2D. Okay. Now how to get all the points in this? Any idea? Any quick suggestion? What is the naive approach? We have n points. We want to know. We have given a box. We have given a range, and we want to know what are the points in this range. How to do it?
By knowing all the coordinates.
Yeah,
And
we know all
then
the coordinates of the point. So yes, so we can just take a point. We can just see whether that point to this range or not. Yeah, you're right. So we are just doing the checking. We are take every point. We check whether this belongs to this range or not. We have given a range. We have given the box. So that will cost us how much time? Order of n time, right? Because we have n points. For each point, we need to do that exercise. Okay. So, but we want to do something better. So, so for that, we need to think for some data structure, and we call this data structure to be static. Why it is static? We are calling because we don't often changing the points, because we are suppose a ray student. I mean the database ray student. We don't often have the new ray student. I mean not frequently, right? So we just want to make some static arrangement. We just want to make some static arrangement on this point, some pre-computation on these points, keeping in mind that it is not dynamic set, because not very often new day student is coming off. But anyway, we'll talk about dynamicity also here. But for the time being, let us assume these points are uh, static points. It is not. Uh, changing. I mean, then nobody insertion and deletion. We are in that case is not allowing in that case. So we first we will try to look for a static data structure. Then we will see how we can have a dynamic data structure for this. So for why we are looking for static data structure, because we are assuming these points are not often changing. Like the, for example, restaurants are not very new restaurants are coming in the city, or not a restaurant is closing. So those type of example applications are there. Okay, so that's why our goal is to do some pre-processing on the points. We are going to store these in somewhere. We have a data structure. We are going to do some pre-processing on the points, so that we can do the search in a we can do the query in a faster way. So we can do lots of query. Once we done something on this database in the pre-processing, then after that in the runtime we will do lots of query. So that is required, because we may have different people have different taste. They can go to the veg restaurant, non-veg restaurant, price is this. So many queries we should able to do with a. So that is the thing. So these points are not often changing. Our database is static database, so you have to do some pre-processing on that to do this. Okay. And for 1D, we will have a dynamic data structure also, which supporting deletion and insertion. So let us talk about some data structure which we already know to handle this problem. Is the problem is clear? So now we will go for the 1D range search. So suppose we have 1D points. We have few points, like we have some keys. We have some records. From these records, we choose one field to be key field. We have seen that, and that based on that field, we are maintaining a data structure, so that we can do the search. We can do the query in a faster way. Okay. So suppose these are the points. These are the given points. So this is a single points like 1D. So these are on the real numbers. Or you can say this is an array. So you have given array of some, we have given some points over in this. Okay. Now we have seen in the last lecture, maybe we have seen the interval tree. So can we apply the interval tree? So what we have? We have some range. So range means we have some. Sorry, this is the range. We have some range, and in that range we want to see how many points are there. So that is the orthogonal range search. So we have some range over here. This is AB, say AB. So here we have a close interval AB. So we have some range over here, and we want to find what are the points at. We want to do the query. So on this query interval. So if you recall the interval search, interval search tree. then if we make these points to be interval, how to make a point to be, suppose this is a point x, how to think this is interval like this, x comma x. Okay, we can represent each point as an interval x comma x, and then we can do the interval search tree. We can do the interval search tree, that if you remember, that is a red black tree, and we have done some argumentation there. In the red black tree we store the maximum element in that subtree, including the intervals, and we have keyed that those intervals with a left endpoint, low of x. Okay, like this. Okay, so basically each points we can think for a intervals with x comma x like format, and then we have a query intervals, and then we can do the interval search. This we have seen, and how much cost it will take, because we know this is a red black tree with some argumentation over there, and each search will take log n time, and if there are k intervals which is overlapping with that, then after getting first interval we have to delete that to get the second interval like this. So this will cost us order of k log n time, and this data structure we have already seen in our previous lecture. So that is the thing. Okay. So that will cost us order of k log n. Any question? Yeah. So now we have to do faster than this. Yes, please.
Sir, what is K?
K is the number of points. We in the interval search, if you remember, if we want to just get a one interval, it will take log n time, because we have to travel height of the tree. That is a red black tree with some argumentation. Now if we have to report all the intervals, so here if there are k many points are lies in this range, if we want to output if we know all the k points, then it will cost us k into log n, because that many times after deletion we get the first interval, then we delete this from this database, from this red black tree, then we do again the search, we will get the second interval, second point, like this. That is the k. This is output sensitive time complexity. K we are assuming the number of points which is overlapping with which is in the range.
Okay.
But we want to do it in k plus log n time. We are not happy with k into log n time. We want to do this. We want to report all the points in this range in the k plus log n time. So can you think for some other way to do that other than this interval search? Can you use some previous technique? We have the previous lectures, like beginning, like sorting. Can you apply sorting on this? Because we can very much assume these points are static points, because is the that is.
Is there apply sorting on either x coordinates or y coordinates and then search
No,
in the
we have only one coordinate. We have only, this is 1D points. So we have some keys basically. We have some keys. Say 5, 6. We have some keys only. Okay, something like that. And then interval. We have an interval like from 3 to 9. How many points are there? Like this. So these are only one coordinate, only x coordinate. So now can you suggest something?
So sorting and then doing binary search.
Yes. So basically what we do, we just sort it. We just sort the points and store them in an array. So we have given an array. We sort it and store it in the array. Now this is a sorted array. Okay. Now we have a query. We have a range AB. Now we do the binary search with A. So suppose it is here, somewhere here in this, and we do the binary search with B, which is somewhere here. So that means we are basically in binary search we are returning the this thing index, right? It may not be here, this A or B, but at least we get some index. So some index where it could be, it is. So some index we get I, and here we get some index j, and we have to return all the points between here, all the points between here. Okay, is this clear? So we got these 2 points. We do the binary search with A, and then it will give us the position, and then we do the binary search with B, another binary search with this sorted. This array is sorted. These points are sorted now. So then we got 2 positions, and inside that, whatever the elements over here, inside that index I and j, whatever elements over here, they are our friend. They are our output. Like yeah. So what is the time complexity for that? How much time is spending for this? First of all, you have to sort it. So if there are n points, sorting will take order of n log n time. So that is the sorting part. And after that, if it is static arrangement, that is if we make it into p-processing time, then what is the time after we make this sorting part? So basically, how many binary search we are doing? 2 times with A and with B. So it will be 2 log n. So this is log n, and after getting this position, if we have to report all the k points, then it will be k plus log n. Is it okay? So this is okay. This is our goal. We want to find it. We want to grade all the points in a k plus log n way. This data structure or this is not dynamic, because we want to, this is a static arrangement. If we have to insert a new element there, then again we have to sort it. So this is one of the drawback of this sorting part. And another thing, can you think this technique, this idea for 2D, this sorting and then going to the binary search?
Sir, doing the same thing with either x or y coordinates, and then in the level searching for the y endpoints.
No, but the x endpoint. So for 2D, what we have the points are x comma y. So these are the points in 2D. Okay, so these are the points in 2D. Now in 2D we have some box over here, and we want to get all the points. Now if we sort it, you'll sort based on which axis?
Either x coordinate or y coordinate.
So you will first sort by x coordinate, then we will do the range search based on the x coordinate. Yeah, so and then again we will sort based on the y coordinate. So if it is 3D, then so that is a botheration of this. So this is not a easier way to extend this data structure, extend this for higher dimensional. So that is one of the drawback of this. We want to do something which is called, we want to introduce a new data structure. Not new, we know this is a balanced binary search tree data structure, but in a different way we will construct it. This is called range search data structure. So we'll know that. So this is a new way we will construct this data structure. Okay. So the idea of this data structure is range search tree. This is called orthogonal range search tree. So idea is we store all the points. Usually we have given points. So let us take an example first. So we store all the, these are the given points. We store all the points in the leaves. If you remember the red black tree, these are nils basically. So the points are, we are storing from the root to the leaf like this, but here it is opposite way. So we are storing all the points into the nils, and then we are constructing the tree. And this is also a balanced binary search tree. So you want to have a this called binary search tree. So we store all the points into the leaf. So these are the leaves. So these are the basically nils. 1, 6, 8 like this. So suppose these are our points. Okay. Now we construct the tree. So what we do, we take this 2 and we have a node over here, then we take this one, then we combine like this. So we construct the tree. Okay. And here all the points are lies in the lips, the nils, in the nils. Okay. Now what are the values we store over here? That really doesn't matter. Only thing we have to make sure that this is a search tree. This is a binary search tree. So you have to have that property that every node should be greater than from its child, from its left child, and it should be less than from its all the elements in the right side. So that is the binary search property. So that it should preserve. Okay. So in that case, what is the value we should put over here in this node? Any idea? What value we should give over here to make this to be search tree? Search tree property we have to maintain because we want this to be a search tree, binary search tree. Can you put 7 over here?
Number between 1 and 6.
Yeah, any number between 1 and 6 will work. But usually we put the maximum value lies in the left subtree. So we put 1 over here. Similarly, we put 6 over here, we put 12 over here, and what we put over here, maximum value lies in the left subtree. So maximum is 14, we put 14 over here. So similarly, this field we put maximum value. So any value between 1 and 8 and 12 will be fine, but we want to have a symmetric arrangement. So we put 8 over here like this. So similarly here also we put the maximum value in the left subtree, which is 26. Then this is 41, and this is this we put the maximum value in the left subtree, that is 35. We put 35 over here. So this is 41 like this. So this way, so this will be the maximum value lies here. Maximum value is 17. So we put 17 over here. So this way we construct. So this is from leaf to the. This is a different way to construct this this tree. Now suppose this is we are doing in pre-processing step. We have some static data. We are making this in the pre-processing step. Now once we have this data structure, then how to do the search? So this is following the binary search tree property, that all the nodes, value of all the nodes is greater than from its left subtree, and is less than from its right subtree. Now suppose we have constructed this data structure. Then after that, how to do the search? How to do the range query? Suppose we have given this query interval 7, 41. We want to do the range query on this. So what to do? We just check 7 is lies here, say, and 41 is here. So that means all the elements between these two will be the all the leaves lies in this will be our output. So that means this 8 and this all the nodes, this all the leaves basically 12, 14, 17, and this is 26, 37, and this is 41. So instead of that, if we just output the subtrees, if we just output 8, 14, 26, and 41, and if we just tell that, okay, our output is the all the leaves lies in this subtrees. We are going to output the subtree, and that idea that will make us help us to extend this to 2D. Instead of outputting each points, we're just going to output the subtree. So we just output a subtree which is rooted at 8. We just output subtree which is rooted at 14. That means this subtree. We will output a subtree which is rooted at 26. That means this subtree, and then we'll finally output. So these are the, and in that subtree you have to go to the leaves to get the final points, to get the points which are lies in this query intervals in the range in this interval. So that is the idea. Why we are outputting the subtree we will come to know. So that will make that will help us to extend this for higher dimensional. Okay. So yeah, so how we are doing this query? We have given some interval xy. I'll write the pseudocode. So we have x1 y1 x1 x2. So this is the query range x1 x2. Okay, we are starting from the root. Then either we go left or go right, because this may be, there may not be any interval which can overlap with this. So what is the condition for that? If the key value of this root is greater than x2, then there will be nobody in this. No, this is key value is the maximum points in the left subtree. So if the maximum is, yeah, if the maximum is greater than from the, so if the maximum is less than x1, that means there will be no interval which can overlap this, then we will go to the right. Okay, otherwise we go to the left. Anyway, so we will do this traversal like this. We start with the root, we will check whether we go left or right. So like this, if we go left, then again we check with this, then maybe we go right, like this. Then there will be a node where there will be something interesting in the both the left part, there will be some interval which is some some points which will be in the right also. So then in that case we have to go both the side to get the points. So this node is called split node. So until we go to the split node, we have to keep on traversal either left or right. We go left if there is nobody in the right part, and then or we go right if there is nobody in the left part, depending on the value of the key and this range. So we traverse. So this way we go and we reach to a node. We may reach to a nil also. I mean leaf node. In that case, we check whether that leaf node is in the range or not. We return that, otherwise we stop. But it may, so eventually we will reach to a leaf node, or we will reach to a node where there will be something interesting in the left and there will be something interesting in the right also. So that node is referred as split node. So until we reach to a split node, we have to do this traversal. So once we reach to a split node, then we have to do left traversal or right traversal, because that means there will be some points in the left subtree and there will be some points in the right subtree also. So let us do the first left traversal. We do the left traversal. Suppose we are doing the left traversal and we check with this node, and if something is there in the left part, that means all the nodes in the right part will be in the range. So that means we have to output the whole subtree rooted at this right node if we are going to left part. Like this we continue, we go to the right. Once we go to the left, that means all the subtree rooted in the right child of this node will be our output. So this way we do similarly in the right traversal. If we have to go to the right from a node, then all the nodes which will be rooted in this left child of this node will be in the range, because we are going to the right here. So we output all these nodes. Suppose these are the nodes, these are the subtrees we are outputting. Okay. So this subtree we are going to output as our this range search query. So we can have a pseudocode for this. Then it will be more. So we have this range x1 x2. We are going to search in this structure. We have a tree, range search tree. We have already constructed in the pre-processing step. I will put all the nodes in the leaf or nils, then we make the tree, and then okay. So we start with the root. Now if it is leaf, then we check whether that is if it is not a leaf, or if it is not a split node. This is the checking for split node. So either it will be go to the right part completely or left part. So if x2 is less than key of w, so x2 means the our x1 x2 is the interval. So this is our x1 and this is our x2, low end point, high end point. Now if the key of w, if key of this value is if x2 is less than this, so that means there will be nobody in the right part, we have to go to the left part. So we do the left traversal. Else if this is the case, then we have to go to the right part, because in that case this interval is completely in the right part. So this way we continue until we reach to a split node, until this condition is violating. Once this condition is violating, or if it is a leaf node, then we stop. So either it is a leaf node or it is a split node. So this node is a split node. Once we reach to a split node, then we have to do the left and right traversal. So that we will just show the left traversal and the right traversal will be similar. So this is the left traversal after the reaching to the split node. Okay. Now this could be a leaf also. If it is a leaf, then we just check the value whether this in the range or not. If it in the range, we output W. Otherwise, we check, we go to the, this is the left traversal. We take this to be V, our left child, and then again we check whether this is a leaf node or not. If it is not a leaf node, we check whether key value of this is if x1 is less than key value of this. So in that case, we have to go to the left again. When we are going to the left again, then all the leaves over here in the range, so we have to output this. We are outputting this tree, subtree rooted at the right. So we just output the subtree rooted at the right, and then we go to the left, and again we do the same exercise. Once we go to the again we are going to the right. Once we go to a left, then all the nodes, all the subtree, all the nodes rooted in this right subtree will be the output. So this is the thing. So until we reach to a leaf. Once we reach to a leaf, we check whether that value that is in the range or not, then we output that. Okay. So this is the idea. So similarly, the right traversal is similar. I'm not. Okay. Now tell me the time complexity for this algorithm. How much time we are spending for this range search query? How much time? This is a balanced binary search tree. So we have given a. So what is the time for this code? This 1D range search, 1D range search query. How much time? Any idea? Other than this pre-processing time. So if it is a, so this is a balanced binary search tree. So what we are doing? We are just starting from the root, and we are traversing, and then we are reaching to the leaf, and we are outputting some subtrees if it is in the range. So that way it is just log n time, height of the tree, because eventually we are traversing from the root to the leaf, height of the tree. Okay. And how many subtree we are outputting? Any idea? So basically we are traversing and we are outputting some subtree. So the time complexity will be order of n log n. Sorry, order of log n. Order of n log n will be for constructing the tree. That is okay. But order of log n is the time for traversing. And so this is to return all this. This way we are outputting all these subtrees. Where we have this leaves are our final output. Leaves are our, where here all the leaves over here are our points which are lies in this interval. So now we have to go, how to get the leaves over here? We have to go to the leaves, and then we have to get all the points. So that will, So that will cost us again k. So this is order of k plus log n if we have to get all the points over here. Now, if we have to do this query, how many points are there? How many points are there in this range? So can you do it in log n time? Can you do some more augmentation in this data structure so that this can be in log n time? If we store the in this, so we can do this augmentation. We can store the subtree sizes in the each node. Then this is a subtree where subtree sizes means we can just do the number of leaves. We can just count the number of leaves over here instead of subtree size. We can just count the number of leaves and we can store there. And that we can just add it up. So that augmentation will help us to get the how many points are there in this, that value k. That value k we can output in the same time, order of log n, to do it if we do this augmentation. Okay, so any question before we go to the 2D? We want to generalize this. We want to go for the 2D. Any question on this data structure, or is this clear? The 1D range search. So what about the space? Space we have n points, so it is order of n, and the p-processing. How to get this tree? So for how many points are there in the leaves? There are n points because we are storing all the points in the leaves, nils, and then we are forming the tree. So height of the tree is log n. So it is basically L log n is the p-processing time. Yeah. So if there is no question, we can straight away go to the. We can straight away extend this for the higher dimension, at least for 2 dimension. That is the idea of this outputting this subtree. Instead of outputting this the points, we can output the subtree, and in that subtree we can go to the points and get the output. Okay, so the idea is like this. So here we are in 2-dimensional. 2-dimensional means we have points like x comma y. All the points are having two-dimensional x comma y, x coordinate, y coordinate. So here we call a primary data structure which is 1D range tree. We store these points in a 1D range tree. We make this data structure in the p-processing, but based on the x coordinate. So these points are having x, y both coordinate. We just ignore the value of y. We just take the key as a x values, and then we form this data structure. This is called primary 1D range tree. We form this range tree based on the x value, x coordinate. Okay, and then we have given the x. So basically this orthogonal insert. So we have given some rectangle. So this rectangle. So these are some x comma. So this is x comma. We can write it. So this is x1, y1. This has some coordinate, and this is x2, y2. X2, y2. Then what is this coordinate? This will be, so this will be y1 is same. This will be x2, y1. This will be x2, y1, and this will be what? This will be x1, y2, like this. We have given some rectangle in a 2-dimensional, given some range, and we have to find what are the points lies in this range. Okay. Now we first have a 1D range tree based on the x coordinate. So if you do the search on this, based on just x1, y1, sorry, x1, x2, because our points are, our tree is based on the x coordinate. Then we'll get all the points which are lies in this strip. This is an infinite strip. Okay, where x1, y1 strip, we have no restriction on. So we can get all the points which satisfying the x coordinate criteria. That means all the points x value is lies between x1 and x2. Okay. So then if we do the range search on this point, suppose these are the output. These are the output. These are the our subtree which are having the leaves with the x value matching, x value in the range. But we want to have a y value also. So if we have another data structure based on the y coordinate. Okay, so this we can get it in log n time. This all the subtrees, and how many subtrees are there? Log n subtrees are there. Log n or log k. Anyway, log n is the upper bound. So log n subtrees are there. So for this, again, if we think for another data structure based on the y coordinate, so that means for each of these tree will be associated with, so yeah, so each of these tree will be associated with another tree where all the points lies over here. So each of these is associated with another tree with the same size. Lots of data structure are going on. We have another, we are doing the another range search tree, secondary range search tree, that is also 1D, but that is based on the y value, y coordinate for all the points. So whatever the points over here, so this tree, so for this point we have a similar tree here which contain all the points over here, and this tree is based on the y coordinate. And now this is again 1D tree, but this is based on the y coordinate. Now we'll do the again range search on this. We'll start from the root. We'll go left, right like this. Then we'll reach to a split node. Then again it will go give us some output on the subtrees, and that output will be based on the y coordinate. We already had a x coordinate match, so based on the y coordinate, so those values which are also matching in the y coordinate, those values are our in the final output. So those will be the matching both the x coordinate and y coordinate. So lots of data structure are going on over here. So we have two, basically we have one primary range search tree. This is for all the points. All the points we are having this structure. So for these points we have similar tree over here, and in that tree, and that tree was made based on the y value, y coordinate. So in that tree we will do the range search query based on the y1, y2, y1, y2. So this is our tree. This, suppose this is our this one. So now again we have to start with the root in here. So we start with this left right. We leave node, split node. Then we go if left. Then all the points over here are the output. So these are the all points like this. So we traverse this side also like this. So these are the all points which is matching also with the y coordinate. So this is the idea. So now let us analyze this. So what is the time complexity? Because we are doing 2 times the range query. One is for on the primary data structure based on the x value, x coordinate. So that is log n. And again on the after getting all the output, we are going to the secondary data structure, which is also worst case log n. So it is a order of log n square for the search, and then to get all the output, all the points, if there are k points, then it is k plus log n square. And space is also similar, which is for each of these points for the secondary data structure. Each of this point we are having another tree. So if there are n points in the leaves, so n log n. So that is the space complexity, and p-processing is just just 2D. So 2 times we are doing this. One is primary tree, that is also n log n, and one is secondary tree, range search tree, so that is also n log n. So it is order of n log n. So you can further for d dimension. So this is a general form for d dimensional query. So if there are another dimension, it will be log n cube, because z on the z we have to do this, and space is this like this. Okay, so this is the all about the range search tree. So this is the, I mean, since we are outputting the sub tree, then it is easier to go there and we do the query in that. Any question before we stop? So this is just one data structure we have discussed in this area. We are not do much on the computational geometry. Is if there is no question, we can stop.